Hello, my name is GISELE Campos, and today I'll present a part of a research project developed at the Federal University of Rio Grande do Sul, Brazil, in collaboration with the multinational petroleum company Petrobras. And it's about the influence of reaction parameters and styrene on the copolymerization of acrylamide with AMPS. With the population growth and high use of energy in our society, we estimate that the energy consumption will see a 50% increase by 2040, and petroleum will remain the main source of energy for the next decades. However, when it's extracted from the underground reservoirs, the pressure of gas is not enough to pull out most part of it. And the fluid injection with a very high viscosity is required. The first polymer used for oil extraction was polyacrylamide, but its homopolymeric form does not present a convenient shear strength and thermal stability. So the objective of this project is to optimize the synthesis of hydrolyzed polyacrylamides. It means the copolymer between acrylamide and 2-acrylamide-2-methylpropane sulfonic acid, or AMPS, and also evaluate the properties of the terpolymer containing styrene. To do so, we synthesized polyacrylamide copolymers containing or not styrene. We isolated and characterized them through different types of analysis, as magnetic resonance of hydrogen, size exclusion chromatography, or SEC, thermogravimetric analysis, and differential scanning calorimetry, both thermal analysis. After testing different reaction parameters, we found that the best initiation system for the polymerization was by using ammonium persulfate and sodium bisulfite at 25 degrees Celsius with a monomers concentration of 10%, and using the monomers of acrylamide, AMPS, and styrene, obtaining more soluble products with higher viscosity, which is what we want. So here we can see the results of hydrogen NMR, confirming the formation of the polymers. Here we have the homopolymer of AMPS. Here we can see the signals of AMPS. Here's the solvent water. So after that, we synthesized the copolymer between polyacrylamide and styrene. And even if it's only 2% of styrene, you can see its presence here. Then we synthesize the polyacrylamide AMPS copolymer. We see AMPS here. And finally, the terpolymer containing polyacrylamide, AMPS, and styrene. Through TGA, or thermogravimetric analysis, we can check composition, thermal stability, transition temperatures, content of volatiles. And through this thermogram here, we can see the loss of volatiles, probably mostly water, until 339 degrees Celsius. And after that, we see a decomposition, which means it's very stable, thermally stable until 339 degrees Celsius, which is very suitable for the use we want. Through size exclusion chromatography, it's possible to confirm that we can increase molecular weight by 40%. We can see here the terpolymer in red, and the copolymer between acrylamide and AMPS in black. So with styrene, we have a higher molecular weight, which is very interesting because of the direct relation between molecular weight and viscosity. So it means that we synthesized copolymers between acrylamide and AMPS with very high conversions, up to 90%. And the insertion of the hydrophobic group styrene was capable of increasing the molar mass and, in consequence, the viscosity of the product. Viscosity analyses are still being executed, especially in saline water, considering seawater, and new compositions are under investigation to increase still more the viscosity. So I would like to thank my supervisor in this project, Dr. Cesar Petzold, my colleagues at Simple Lab, Graziella and Marco, Federal University of Rio Grande do Sul, and the company Petrobras. And thank you for your attention.